welcome to the last SPAAM seminar of the term, and we have our very own Jack, who will be talking about acquisition functions in Bayesian optimization.
Super. Thank you very much. It's I'm on microphone. I'm not used to this because I organised the seminar all of last year and never spoke at all. This is my first SPAAM seminar, so it's quite exciting for me. Today I want to talk about what I do, but from a sort of introductory perspective. So I'm not going to do too much of my research, but I'm going to start with the things that I learned at the beginning of my PhD and why I think it's a really cool topic to study. So what is Bayesian optimization? What's it actually for? Why should you care? The optimization is the key word. Bayesian is a bit of a rogue one in there. It's a technique for solving expensive optimization problems, where expensive might mean it's a simulation that takes a long time to run and you want to find the best inputs for it. Or it might be that you're trying to do experiments that cost a lot of money for some reason. So maybe you have to pay someone or use some expensive equipment. So there's some reason that you want to not evaluate this function very frequently, but still want to find the best inputs for it. We need to, if we're going to not evaluate it that often, we need to be able to actually learn something when we observe it. So we're going to assume it's continuous. So this means that when we evaluate the function at a certain point, we're going to learn basically that nearby it's going to be a similar value. Assume that gradients aren't available. So typically a simulation, you run a fluid simulation or something, you won't get a gradient out, you just get a value. So and similarly if you run an A/B test online. So we're going to assume that gradients aren't available. If you are lucky enough to have gradients, then use a gradient-based method. It'll probably do better than Bayesian optimization. There are some Bayesian optimization methods that use gradients, but the majority will just ignore any gradient information. We're going to assume the search space is low dimensional, where low is sort of maybe at most 15 or 20. So if we're assuming that nearby points give us information like about the nearby function value, so if I evaluate it here and I know nearby, then nearby better be enough points to be worth it. But in a really high dimensional space, there's just a lot of space. And so if you pick any two random points, you're likely that they're really, really far apart. So if you've got a distance-based way of saying how similar are these points, it's not going to be very useful to just evaluate a handful, because you won't have covered hardly any of the search space. So that's a lot of things that aren't really allowed. Oh, I should say, by the way, there are some Bayesian optimization techniques that do tackle higher dimensional search spaces up to sort of 100 or a couple of hundred dimensions, but I'm not really going to talk about them today. So what is allowed? It's a global optimization method, so the function can be multimodal. So your typical optimization methods will do maybe gradient ascent. They'll climb to the top of the hill. If you've got lots of local maxima, then you'll need to do that from a lot of different places, a lot of different starts. You'll find a few maxima, and then you pick the best one. Whereas this one's just going straight for the global optimum. And observations can be noisy as well. So maybe you've got a stochastic simulation and you want to find the best value on average. Well, if you a noisy observation, that's kind of like a noisy observation of the mean when you sample it then. And normal gradient-based methods won't do as well with a noisy evaluation, whereas Bayesian optimization can tackle this. Oh, and that's an example of your black box function with the star being the point that we're trying to find. So here are some real examples of this. So simulation optimization was it's a big source of problems, and it's one that I mentioned before. So if you've got, say, you want to find the best design for a wind turbine blade, you've got, say, 20 parameters to control its shape, so its length and sort of cross-sectional profile, and you can run some experiments using fluid dynamic simulations, but they take several hours to run, and you want to find the best one, so you don't really want to run too many of them, so you want Bayesian optimization. Similarly, hyperparameter tuning is a big one, and when you train a neural network, it can again take several hours, and you want to find the best hyperparameters, and so you want to do it in as few steps as possible. And I think people even use it in wet labs. So if you're designing what experiments to do with a biology experiment, it takes maybe even a week to run the experiment. You want to make a sensible decision, so some people are using Bayesian optimization to do that. Specs, not many, but some people. So how can we do this? The obvious thing to do is to throw a load of points down, say on a grid, or just to scatter them randomly, evaluate the function at all these points, and then pick the best one. But that doesn't actually do that well, because a lot of these points are really bad values, and you could probably have guessed they were bad values if you saw some nearby points. So the idea in Bayesian optimization is to choose the points one by one, and then use what we've already seen to inform us as to what's going to be the best one to sample next, what's going to give us the most information about this optimum. And in order to do this in a principled way, we need basically a mathematical way to capture what we already know about this function, which is going to be a Bayesian sort of random function notion. So I've drawn here what we want, but I haven't told you really what that represents yet. Anyway, so assuming you have this, the overall Bayesian optimization loop says you're going to start by collecting some initial observations to get an idea of what the function looks like. So that's these red crosses here. Then we're going to model the objective with this mysterious random function. So this is the blue stuff. So you've got sort of a guess at what it is, but also some uncertainty around that guess. So you know what it is at the red crosses, but it's really wide elsewhere. And then you need to choose where you're going to observe next. So somehow we've got to turn this into a next point to sample. And we're going to do this using something called an acquisition function, which basically tells us how good a point is. So here it's good because you're near a high point here. And so yeah, being slightly near that high point means it's high. And then over here, you've got a lot of uncertainty. So while the prediction is quite low, there's so much uncertainty that it could be high. So there's two peaks, and then this is the higher one. And in this case, it would sample there next. So coming up with what this acquisition function, how you actually write it down, how you optimize it is the subject of this talk. And then you repeat these two steps. So you model it, choose the next point, you observe the next point, you go back, you model it again, you observe the next point, etc., etc. And then you give your final recommendation back to the person who wanted to know what the best simulation were. So the magic random functions that I talked about are formally Gaussian processes. They can be a bit mysterious because they're infinite dimensional objects. So I thought I would go through this again. I thought when I first saw this this explanation, I thought it was a really good explanation. So I'm going to try and repeat it and probably not do it quite as well, but hopefully still an interesting one. You've probably heard that a Gaussian process is a stochastic process where all the finite dimensional distributions are multivariate Gaussian. But in order to use that, you can't really sample an infinite dimensional process, and it's not intrinsically clear what these things look like. So I thought I'd start from saying start by showing you how you can generalize a multivariate Gaussian into a Gaussian process by just increasing the dimension really high. So if the simplest example that I could draw with two-dimensional, where it's still interesting basically, is a two-dimensional problem. So you've got some Gaussian random variable, and suppose we look at the red point there. I can plot that nice and easily. If I sample the Gaussian process again, maybe I get the purple one, I can plot it easily. But if I want to extend to higher dimensions, then I'm not going to be able to plot like 3, 4, 5 dimensions on a plot like that. And I'm going to use these parallel coordinate plots where I'm plotting the first coordinate here and the second coordinate there. So for the red one, the first coordinate is central, the second coordinate is high. So that's kind of central, and then that one's high. And similarly, the purple one matches up as well. So that's what these plots are. And then if I just a single sample now, so this is two-dimensional, one sample on of the multivariate Gaussian, and I've plotted a covariance matrix next to it as well. So this is actually a different covariance to the one on the previous slide, but it's one that's going to be able to generalize up to higher and higher dimensions. So yellow is perfectly correlated because a point is perfectly correlated with itself, and black is, or in this case, almost uncorrelated because I'm imagining these are far away. And then I can add a third dimension. So now this is a three-dimensional Gaussian process with this covariant Gaussian random variable with this covariance matrix. Again, almost all the points are uncorrelated because I'm viewing this as quite far apart. But as I add more and more samples, the covariances are going to get closer. So if I take a four-dimensional multivariate Gaussian, again, and 5 and 6. And then you start to see that the closer points are more correlated with each other, and it's starting to look more like a function. And we can go to say 50 points, and then eventually you just take the limit, and you've got something nice and smooth, which is nice. And then your existence theorems for Gaussian processes tell you that this basically does converge to something, and I'm not doing something stupid by doing this. So to generate these samples of a Gaussian process, you just sample, say, a 100-dimensional Gaussian process, and you can plot it like that. And instead of a covariance matrix, now you have a function. So this is continuous, basically. So between 0 and 1, and you the points that are near each other are correlated, and points that, as you get further away from each other, are less and less correlated. And that was one sample, but you can sample it lots of times, and you get lots of different functions. Then that can be it's quite a good way of viewing it because it tells you the correlations between the samples, but also it's a bit noisy. So people tend to just plot the mean and the marginal variance. So that's what this blue line is here. So the blue line here is the mean. It's only 0 mean in this example because I picked a simple one. and the covariant, and people either plot the standard deviation, or in this case, I plotted 2 times the standard deviation, so it's sort of a 90% credible interval around it. And that's what these plots formally are. And at this point, I'll introduce this notation, which says that we say that f is a Gaussian process with a mean m and a covariance k. Like a Gaussian random variable is a function of both the, is it fully determined by its mean and its covariance, a Gaussian process is fully determined by its mean function and covariance function, or the kernel function. So there are some hyperparameters that typically come when you're modeling with the Gaussian process. So maybe the parameters are the sort of what the actual values of the process are, but the hyperparameters are, say, like the length scale and the output scale. So there are lots of different choices of kernel, and I'm not going into too many of them here, but they all generally come with at least these 2 hyperparameters and maybe some more. So if you start with a Gaussian process, you can imagine if you've got these samples and you sort of stretch them out, then you get something that looks like this. So this is modeling the same thing, but with a longer length scale. Or similarly, instead of stretching them that way, I can stretch them this way, and you get a bigger output scale. And this is all just done by translating this covariance function. So here I've plotted that kernel as a function of distance. So if you've got what's called a stationary covariance function, then like the ones I showed you before, we hadn't conditioned on any observations, so it's just based on distance apart that things are. And so here you can see the 2 that are with a smaller output scale start lower down, and the 2 with a higher output scale start further up. And then the ones with a shorter length scale drop off much quicker, and the ones with a longer length scale drop off slower. So we've got these hyperparameters basically, and we need to be able to fit these to our data while we're doing the Bayesian optimization loops. We've got some data. We want to do the modeling step. That involves picking a length scale and an output scale, and generally people do this with maximum likelihood estimation. So you've got some data, you've got a model, and then what's the most likely model to have generated? Which model will have generated the data, given the data the most probability? There are different choices for the kernel, and I haven't got a slide on that, but a typical choice is a Mattern kernel, which is what I've plotted here. I think it's a Mattern 5/2, which are differentiable and twice differentiable, but no more. So they're good at modeling real-world problems, because the canonical choice of the sort of super C-infinity smooth kernels aren't really very realistic of real-world problems. So these ones are a bit less smooth. They can get around, but they're still twice differentiable, but they can get around about the right number of corners for a real-world problem. So if you do start modeling with a GP, then this is probably a good one to start with before you know anything else. So this is of the Gaussian processes part of the section of the talk. But I wanted to just give you a few useful resources that I really liked when I was learning it, and I can share these on the team afterwards. But there's a really good summer school held in Sheffield, and they've got a lot of videos online, and I watched quite a lot of these videos while I was learning about GPs, and they do a very good job of explaining what I've done in lots more detail and better ways and over a longer period of time, and with a lot more different extensions, such as what you do if you've got tons of data and your GP gets really slow and things like that. There's a fun interactive visualization where you can see the effect of changing the length scale and the output scale, and say if you want to say it's a Bayesian model, so you can condition on your observations. I should have said this earlier. It's a Bayesian model, so you can condition on your observations, and it will be obvious in the plots that I showed before and the ones that I'll show after, how you can say, with a little bit of linear algebra, okay, I've observed that the Gaussian process must go through this point, so it's a Bayesian model. You condition on that value, and then you can see the mean goes through that, and the variance gets lower as it gets closer, and then bigger as you get further away from these observations. And you can see interactively on this website. Really quite cool. And then this is the canonical text. So if you want to go and read something, a chapter a night or something, then this is the place to start for GPs. So the bit that I promised to talk about is acquisition functions. So these are the things that help us. Now we've got a model of what we know about the function. How are we going to actually use that to make a decision about where to sample next? So the acquisition function tends to, is a rule basically for turning that into a next sample. And the plot that I showed you before had a sort of a goodness rating of all of the inputs. So some were good and some were bad. But actually the first acquisition function I'm going to show you, here we go. So here's some are bad, and I should say that the important it's got to trade off between exploration and exploitation. So this was also in the title book. we can either exploit the fact that we know this point is quite good, and so maybe nearby it, it's going to be also a good point. So there are hills here and here because we know the value there, so there's no point evaluating there, but nearby it might be higher on one side or the other. Or the fact we really don't know anything at all over here means that this is quite a good area to look at as well. And in this case, not quite as good, but the acquisition function's job is to trade off between this exploration over here and exploitation. And the first, so this is a nice plot that tells you how good each point is, but the first acquisition function I'm going to show you doesn't actually generate a plot like that. Instead, it's a really simple idea that just says, okay, we've got a random function, why don't we sample it and then just use its maximum? So probably, if the maximum is likely to be slightly nearby the point that we observed, like, then that's going to be a good point. And then some of the time that maximum will be over here, and some of them it will be over here, and then some of them maybe it will be over here. And the ratios will generally be quite good. And so it's naturally trading off between exploration and exploitation, just based on the fact that the samples are random. So each time you resample, you get a new GP, and probably it will sample a different place in the search space. It's really simple. It's also really fast. So people use this in high-dimensional Bayesian optimization. I think this is the only thing I'm going to say about high-dimensional Bayesian optimization. But when your dimensions get bigger, your amount of data needs to get bigger as well to be able to model in that sort of space. And everything gets really slow. And so you need a really fast acquisition function to be able to cope with that sort of problem. So people that used other acquisition functions as well, but the one that's best is called turbo, or maybe there's some variants that have gone beyond turbo now, but they generally use Thompson sampling to achieve that. And it extends to batches of observations really well as well. I'd mention this because it's a natural place to do so. But and a twist on the normal Bayesian optimization problem is that suppose you're training your hyperparameters of your neural network, and you've actually got access to lots of clusters and lots of computers in the cloud, and you can train, say, five times at once or something. Which 5 should you pick? So it's not just which next experiment, but it's which set of experiments. And you can just take 5 samples and look at the maximum of all of them. Probably they'll be spread out. Maybe you'll get a cluster and you'll get unlucky, but over the whole Bayesian optimization, you'll still do a reasonably good job of exploring the input space. This one extends very easily. Others can be extended, but not quite as easily. The next one I want to tell you about is called expected improvement, and this is the most popular choice. So if you're starting off with Bayesian optimization, it's probably the one that you should use first. And then if it doesn't work for some reason, like if your problem's too esoteric to make this one work, or if you're getting bad results with it, then try something else. But as a go-to for where to look for first, if you don't know anything better, then this is a good one. And it asks the question, sort of, I've got these like n samples, and at the end of the optimization, you're just going to return the best one that you've observed so far. And expected improvement asks the question, well, if I've just got one more sample that I can take, how am I going to get the best? What's going to be the best one to maximize that thing that I'm going to return at the end? So that's a bit of a confuddling way of saying it, but in terms of the equation, and I said I wouldn't do the equation, but if we're trying to say, well, how good is it to evaluate at x, we can take variable as the function. F star is the best that we've observed so far, so it's this dashed line here. And we say, okay, this is the improvement, which is basically if it's positive, it's the difference, and if it's negative, then it's 0. And we want to say, look at the expectation of that improvement, hence the name expected improvement. So on the picture, which is maybe clearer, x here is this line here. The mean is there, and we're basically saying this is the probability distribution associated with sampling there. So if we sample here, we might get high, we might get low. This is the density. And then this shaded bit is the area that will beat the current best point. And we basically want to take expectation of points over this area. So we count as 0. If you're above it, you count as the amount you're above this line, and then integrate with respect to this density. Oh yeah, it's also got an analytic formula. So this isn't the formula. For the formula, you can write it in terms of the density and cumulative density function of a normal distribution. But it means that it's really fast to optimize and fast to evaluate. Not all acquisition functions are that fast. In order to optimize it, you use something like a gradient-based method, so something like LBFGS. So you can start it, and it's multimodal, so they're already you exchanged one multimodal problem for another, but you can evaluate. You can start it here, and you can start it here, you can start it here, and you can do some gradient-based method, and one of them will find the best, and then you can say, okay, this is the point that I should evaluate in this case. So yeah, when you want to take your next sample, you model the function, you calculate, you can start your optimization to calculate EI at different points. You do the LBFGS optimization, and then you find the best one to pass on. There's one more that I wanted to tell you about today, which is slightly more complicated, but and there are lots more that I won't tell you about. But this one asks the question, okay, so it's like expected improvement, but what if we don't need to return a point that we've actually observed? So instead of, what would that mean? Instead of returning one of the red crosses at the end, we could actually just return the maximum of the posterior mean, so the maximum of the blue. In this case, it's not that much better. In some cases, it might be a lot better. This changes it. So this means that instead of saying how much am I better than my current best, you're instead saying, suppose that I evaluate at x, I could get any of these values here. If I got this one, then my posterior mean is going to change from this blue line to this green line. And then the maximum of this green line is actually higher now. And that difference between the maximum of the blue line and the maximum of the green line is what we give to the value of the acquisition function. So the one that's going to improve the maximum most over the whole optimization, over the whole search space, sorry, is going to be the point that we want to evaluate. And in terms of equations here, just to explain the symbols, but not much more, the m's are the posterior mean. So mn is the posterior mean now, and mn plus 1 is the posterior mean after we observe the next point. And we're saying, how much do we expect the maximum of this posterior mean to increase if we were to observe the next point at little x? It naturally handles noise. So expected improvement didn't really handle noise. You notice these plots, I've drawn the uncertainty going to 0 around the red crosses. Whereas knowledge gradient, if you had noise, it would handle noise. So the point is the best point might be, you might observe the best point as being like accidentally much better than it actually was. If you were to look again, it might not be that good. And expected improvement would keep saying, oh, we're never going to beat that perfect one we saw before, so it's going to make silly decisions about where to sample next. Whereas knowledge gradient isn't using the values of the observations, it's instead using the posterior mean. So if you get more and more evidence that actually that point is a bad point, then it's going to start thinking, oh, maybe we should sample near that again because we could still beat it. And it also handles partial observations. So this is something I'll come on to at the very end of the talk. If you've got basically it doesn't matter what you condition on. So in the formula here, you're conditioning on I haven't written it down, but you're saying, suppose I observe the value of the acquisition function here, but maybe you observe something that only tells you half about that value somehow. So maybe it's the case I'll talk about later is a multiple objective problem, but there are also cases where you've got, say, a cruder version of your simulation. So maybe you've got a low fidelity version of your fluid simulation that runs much faster and a high fidelity one that runs much slower, and your low one is kind of correlated with the high fidelity one, but not as well. So you can say, if I observe the low one, it tells me something about the high one, but how much? And knowledge gradient basically it naturally copes with that sort of information. It requires Monte Carlo. So I emphasized that expected improvement had an analytic acquisition function. So it was really fast. Knowledge gradient needs to do some sort of Monte Carlo or discretizations. There are some that work at some methods that are kind of analytic if you just use a discretization in a lower dimensional space. But if you've got that lower here means like 2-dimensional. If you want to scale to sort of 10 dimensions, say, then you generally have to do something quite expensive to optimize the knowledge gradient. So it's slower. So I wouldn't say use this one out the box. I would say use EI out the box, unless you've got some sort of partial information, noisy type problem, then maybe consider knowledge gradient. Okay. And when you're optimizing this acquisition function, again, you've got something that looks like what we had before. It's a bit smoother, but still you're going to have to do multi-star LBFGS. Because it's a stochastic, it uses Monte Carlo, you've now got a choice between either having a stochastic gradient based optimization, a stochastic gradient based optimization, so you can use something like Adam to optimize this and get different estimates of the gradient and the function value at each point. Or you can use a deterministic based method. So you can use the reparameterization trick to sort of fix some base samples. I mean, all of this is quite abstract. And then basically, it's faster to use these deterministic gradient-based methods if you do this reparameterization trick. If you're using it, then I would go that route rather than the other route. In BowTorch, that is the default anyway, so you'll be good if you're using BowTorch. And this is quite jaggedy here, so I'll just point out as well that because of the additional computational complexity of having to do the Monte Carlo and the inner optimization and stuff in this one, even this plot produced something smooth. So the actual knowledge gradient is smooth, but it hasn't, numerically, it's been a bit unstable here already. So another reason to not make it your first choice. And then I've told you about, there's a whole acquisition functions. I've talked about the Thompson sampling and the expected improvement and knowledge gradient on the left, but there are lots of other acquisition functions you could want to look at, such as entropy-based ones, where you're saying instead of caring about sort of improving the maximum of your objective, you're instead trying to reduce the entropy in that maximum, so reduce the uncertainty somehow in what the best next input is, or perhaps the best output value. There are lots of variants on this. It works similarly well to knowledge gradient for sort of noisy problems and partial information, and like knowledge gradient, it's also really slow because you've got a lot of Monte Carlo and internal optimizations going on. One that came from the multi-arm bandits literature is this upper confidence bound. So it's got some good theoretical properties associated with it, but it's generally, there seem to be two sort of sub-communities of Bayesian optimization. Some of them will use upper confidence bound and do a lot of theory and say, okay, here's your regret bound, and some of them won't. But generally, you're saying, if you've got your Gaussian process, you can take your sort of 90% confidence interval above it, and that will reduce as you sample there, and eventually you converge to the true. As you converge to the true value, you will eventually find the best value of your hidden function. I won't talk much more about it. Probability of improvement here is a very simple method. It's like expected improvement, but just the probability instead of the expectation. Not as good, but it's an important early acquisition function that people used. And here are the things that I kind of hid from you before. So acquisition functions were multimodal. You could see this one at least. So we've exchanged one multimodal problem for another. But the good thing now is that the function we're evaluating is a lot cheaper. So we're allowed to do sort of multi-start gradient descent and things like that. It can have lots of flat regions. So if you're doing gradient ascent and you start in a flat region, it's not really going to work. If you've got too many flat regions, maybe all your starts don't work. So this is a problem. You tend to have to sort of scatter tons and tons of points around your search space and then just pick the ones that are best to start from. And it can be computationally very expensive as well. So in my research, I find that it can take me sort of, 3 minutes, 5 minutes sometimes to optimize the acquisition function. So if your objective function isn't like an order of magnitude slower than that, then there's no point doing Bayesian optimization. But if it's on the order of hours, then it makes sense to spend a few minutes optimizing the acquisition function. And I also didn't tell you how you choose your initial samples. I just said you start with some initial samples in step one. But you could choose them randomly, but it would be better to choose them sort of spread out. So people tend to use these, not independently at random set of points that are guaranteed to be spread out. So there'll be either a Latin hypercube or a Sobel sample. And I haven't got a picture here, but they don't clump together in the same way that independently selected points would clump together. It can be a lot more efficient. So just to finish up, I was going to tell you a bit about what I've been researching for some of last year. It's a multi-objective problem. So all the examples I gave you so far have had only one objective, where it's obvious what the maximum is, but now you've got two things. So maybe you're trying to decide what the best, design for a car is, and you want it to be aerodynamic, but you also want it to be safe in a crash. And these things aren't necessarily going to be optimized at the same point, and so you're going to have to find some designs will obviously be better, some will be faster and safer, but some designs you have to trade off between being fast and being safe. And so this picture is supposed to represent, of your two objectives, these are the possible designs you could have. And then these are the ones that are, in some sense, best, but they're all best. Like, it's not a single point. And this is it's called the Pareto front of optimal trade-offs. And the aim of the game is to find this in as few samples of your objectives as possible. So this is interesting in my case, because I'm saying, what if you can evaluate your objectives separately? So you don't need to always evaluate both your objectives, but maybe if one of them is wiggly and cheap, and one of them is smooth and expensive, then we don't need as many observations of the wiggly one, of the smooth one, sorry, because we know it's smoother, or we can learn it's smoother. And because it's expensive, we save quite a lot of time or cost or budget, basically, by not evaluating it. So there is scope to make sensible decisions about which objective to evaluate in order to improve how Bayesian optimization works. And I applied knowledge gradient to this, so that's why I picked it as one of the three I told you about before. But you can see, basically, on this plot, if you've got always evaluating both your objectives, and this is now cost, not number of samples. If you're always evaluating both your objectives, you do this well. And then if you're allowed to choose which objective to do with knowledge gradient, it can converge to zero regret here. So this is sort of difference in hypervolume from between what you recommended and what's actually best. Basically, you want it to go to zero. And this goes to zero faster. And I did this, and then I discovered that someone had already solved it with entropy, and then later on, someone also solved it in another different knowledge gradient way, and they all do about basically the same. So the difference is basically using using Bayesian optimization to decide which objective to evaluate next, and then the way in which you do it is not that important. So after that point, it's more important how fast your acquisition function might run. Is it computationally feasible or something like that? So thank you very much. And do you have any questions?